Okay, welcome everyone. Thank you so much to our speakers for waking up extremely early to accommodate our time zone. Qing is going to be talking about trigonometric Lie algebras, affine Lie algebras, and vertex algebras. Feel free to start whenever you're ready, Qing. Thank you so much.
Okay, thank you. First, I would like to thank Frost's invitation and organization for the Angels and Thomas. Today, I will talk about the trigonometric Lie algebras, Affine Lie algebras, and the vertex algebras. We know that vertex algebras from their origin have deep connections with infinite dimensional Lie algebras. Today, I will talk about the connections between trigonometric Lie algebras and the vertex algebras. First, I will realize the trigonometric Lie algebras as the covariant algebra of Affine Lie algebras. Then, based on this, I will establish the connections between trigonometric Lie algebras and the vertex algebras through certain module categories. So my talk will be divided into two parts. First, I will explain some basics about the Affine vertex algebras and their modules. Maybe all of you are familiar with this part. And second, then I will present our results about the connections between the trigonometric Lie algebras and the vertex algebras with the action of group, what we call the gamma vertex algebras. So I will start from our main objects called the trigonometric Lie algebras. Trigonometric Lie algebras has four types called A, B, C, and D. They are a family of infinite dimensional Lie algebras involving trigonometric functions as in their structure constants, which was introduced in these two physics papers. They are the trigonometric deformation of the area preserving algebra of the torus. Let's see the definition of the trigonometric Lie algebra of type A with rank 2. It is infinite dimensional Lie algebra with the generators A alpha m for these two integer valued index and subject to these Lie relations. We view this trigonometric Lie algebra of type A as the Z-graded algebra with respect to the second index. This algebra is essentially the quantum torus Lie algebra. Quantum torus, we'll know that they are the non-commutative torus. When we see it as the Lie algebra, the trigonometric Lie algebra is isomorphic to the quantum torus Lie algebra, and they are related by the correspondence from the generators of the trigonometric Lie algebra AMN to the elements of the quantum, these elements of the quantum torus. The quantum torus plays an important role in the classification of extended Affine Lie algebras. We know that for the extended Affine Lie algebras of type A with the rank large O equal to 3, the coordinates algebra can be quantum torus except the Laurent polynomials. And the representation theory for the quantum torus or trigonometric Lie algebras have been studied mainly on these two papers. in this paper, they give the authors give the vertex operator constructions for the irreducible highest weight module with level 1 for the combinatorial Lie algebras. And Katz and Riddle, they classified all the irreducible highest weight module with finite dimensional weight space of the trigonometric Lie algebra in this paper. So similar to the construction of the finite dimensional classical simple Lie algebra case, trigonometric Lie algebra has also has 4 types called A, B, C, and D. And type B, C, D can be realized as the fixed point subalgebra of the type A trigonometric Lie algebra on the involutions. We see that from the involution tau B, tau C, and tau D, we can realize the type B, type C, and type D trigonometric Lie algebras. Now, what we do is to study the trigonometric Lie algebras and their module categories in the context of vertex algebras. So the problem is how can we associate the trigonometric Lie algebras with vertex algebras? And then after this connection, how to establish the equivalence between the module categories of the trigonometric Lie algebras and their corresponding vertex algebras. So first, let's record the association of Affine Kac-Moody Lie algebras and vertex algebras. We start from a finite dimensional simple Lie algebra. So we have an Affine Kac-Moody Lie algebra G hat. We can get Affine vertex algebra from the generalized Verma module of Affine Kac-Moody Lie algebras. So this is a universal Affine vertex algebra. When we write all its generators as the generating functions as AX, Lie proved in 1996 that any restricted module categories of the Affine Kac-Moody Lie algebra are one-to-one correspondence to the module category of the Affine vertex algebra, this VG hat L0. So this is on the level of the universal Affine vertex algebras module and the restricted module for the Affine Kac-Moody Lie algebra. Furthermore, if we write LG hat L0 to be the simple quotient of this universal vertex algebra, Dong, Li, Mason proved the following result, which gives the module category correspondence for this simple vertex Affine vertex algebra to the integrable module categories of Affine Kac-Moody Lie algebras. Furthermore, if it is, we consider the irreducible module for this simple quotient vertex algebra, then this category for the Lie algebra is integrable highest weight module for Affine Kac-Moody Lie algebra. So this is the association of Affine Kac-Moody Lie algebra and vertex algebra and their module category correspondence. So, in the association of vertex algebra and their modules to the Affine Kac-Moody Lie algebra or Virasoro algebra, it is essentially the canonical generating functions are mutually local. So what is this mean? So from the local system, we can abstractly construct the vertex algebra and its modules. That is for W vector space, and we let EW to be the home space of all maps from W to the truncated, the space of truncated Laurent series. A subset or subspace of EW is said to be local if there exists, if for any two elements in U, there exists a non-negative integer such that after multiply the polynomial x1 minus x2 to k, they are commute. In 1996, Affine Lie proved that any local subset can canonically generate a vertex algebra with W a module under this vertex operator operation. So this is so that is to say, from the local system, we can abstractly construct a vertex algebra and its module in this way. But the difficulty is how to identify these as abstract idols. So for the Affine Kac-Moody algebra case, we know its Lie relation for the generating function is written as this. So we can easily to see they are local for the generating functions. So it can be proved the abstract vertex algebra constructed from these local operators are nothing but these universal Affine vertex algebras. So this is the story for the Affine Kac-Moody Lie algebra and vertex algebra. Now we turn to our main objects, that is trigonometric Lie algebras. Trigonometric, we recall that the type A trigonometric Lie algebra is has the following Lie relations. It has one dimensional central extensions, and so follow the standard step, we can write its generators as the generating function and transfer the Lie relation, this Lie relation to this Lie relations. And with an observation is that we see these operators in trigonometric Lie algebra, after doing the Lie bracket, they are not closed. There is a scalar, this scalar in red color comes in front of the variables. So they are, for these operators, they are not closed. So when we consider such cases, we need to consider the vertex algebra comes with a group action. So we need to generalize the local system to the gamma local system. So what is called the gamma local? A subset of this EW is called the gamma local. For gamma is a subgroup of the set of all non-zero complex numbers. If for any two elements in U, there exists the polynomial has the form like this, x1 minus alpha x2 for alpha in this group top. So when after multiply the polynomial like has this form at px1, px2 generated by these polynomials, x1 minus alpha x2, this kind of polynomial, they are commute. So this we call the gamma local. So when we consider the operator has the scalar in front of its variables, the vertex algebra comes with a group action. So Affine Lie in 2006 introduced the vertex algebra with a group action called the gamma vertex algebra. it is a vertex algebra equipped with two group homomorphisms. One is from gamma to the general linear map of this V. And the other is group character. And these two group homomorphisms should compatible with the vertex operator YVX. So this is compatibility conditions. So after the definition of algebra, it should has a corresponding module definition. So first we record the Quasi module for a vertex algebra, which generalize the module, the notion of module for the vertex algebra. It's just substitute the Jacobi identity in the definition of the module of vertex algebra into this called Quasi Jacobi identity. That is, the polynomial is substituted by this general polynomial fx1, x2. And in the general notion of module for the vertex algebra, this polynomial is x1 minus x2 to the non-negative integer k. So we generalize this module definition to the Quasi module, just replace the Jacobi identity for the module to this Quasi Jacobi identity. So after this definition, there is a corresponding module category for the gamma vertex algebra, what we call the an equivalent Quasi V module. So it first should be the module for Quasi module for V viewed as a vertex algebra. Then it should satisfy these compatible conditions for this for the group homomorphism defined in the algebra. And the polynomial at this time is it has the form like x1 minus alpha x2, like this case. It has such a form for the polynomial. So this is the module, the notion of the equivalent Quasi module for gamma vertex algebra. So similar like from the local system, we can abstractly construct the vertex algebra and its module. So Hyson Lee proved from the gamma local system, it can abstractly construct a gamma vertex algebra with WN equivalent Quasi module. So let's see an example of gamma vertex algebra to see the gamma vertex algebra is indeed exists. So we know that a Z-graded vertex algebra is a vertex algebra with a Z grading and satisfy these grading conditions. If we let gamma be an automorphism group of this Z-graded vertex algebra, preserving this Z grading, and let chi to be the group homomorphism. If we set this RG in the definition of gamma vertex algebra to be the chi G up to minus L0 G, this L0 is the linear operator on V, defined by L0 acts on the grade N subspace to be N. Then this V becomes a gamma vertex algebra. So if this has a vertex operator algebra structure, it is naturally have a gamma vertex algebra structure. So now we can realize because our our final goal is want to associate the trigonometric Lie algebra with the vertex algebra and find the module category correspondence between them. Now, first, we need to realize the trigonometric Lie algebra as the covariant algebra of Affine Lie algebra. Then we use the connection between the Affine Lie algebra and the vertex algebra to establish the connection of the trigonometric Lie algebra and the vertex algebras. So we let GL infinite to be the associative algebra of all doubly infinite complex matrix with finitely many non-zero entries. And we can see this GL infinite is a Lie algebra with the basis of this EMN is the unit matrix with only non-zero entry is MN, which is 1. And it has such Lie relations between the from the product of the matrix. So we equip this GL infinite with a non-degenerate symmetric associative bilinear form from the trace of the product of two matrices. Then we can see that the additive group of integers as can act as the automorphism group on this Lie algebra GL infinite. Then we consider the subalgebra of this GL infinite, that is the index, the sum of two index M and N to be even. We consider this is the subalgebra of GL infinite. And we can write its basis as G alpha M. This is the symbol to denote the matrix E alpha plus M, M minus alpha. Then we can see that there is also a non-degenerate bilinear form on this A by restrict the bilinear form on it. And also this additive group of integers preserve this subalgebra. That is, A is stable under the action of this additive group of Z. So motivated by the gamma conformal algebra introduced in this paper by Katz and his co-authors, Hyson Lee proved such results about the covariant algebra. So what is covariant algebra? It is the generalization of it is similar like the generalization of the twisted Affine Lie algebra from the untwisted Affine Lie algebra. So we see that G is a Lie algebra with symmetric invariant bilinear form, and that gamma to be a subgroup of this Lie algebra preserve this bilinear form, and let phi to be a linear character. And after the action of this group gamma, the bracket and the bilinear form should satisfy these conditions. Then we define the new bilinear operations on this central extension of this loop algebra. Then the subspace linear spanned by the elements of these elements is the action of G act on the elements of A tensor Tm. Then this is a two-sided idea of this non-associative algebra under these operations. So the quotient algebra, we denoted by G hat gamma. This is a Lie algebra. So if this gamma is, the group gamma is finite, then this covariant, well, so we call this Lie algebra is a gamma covariant algebra. It is a quotient algebra. If this gamma is a finite group, this gamma covariant algebra is isomorphic to the fixed point subalgebra of G hat under this finite group gamma. So from this, we see that we know that how to get the twisted Affine Kac-Moody Lie algebra from untwisted Affine Kac-Moody algebra. It is the fixed point of the untwisted Affine Kac-Moody algebra on the diagram automorphisms. So this covariant algebra generalize this. So it is the quotient algebra, and this gamma can be infinite group. So next, we want to realize our trigonometric Lie algebra to the covariant algebra of Affine Lie algebra. So our Affine Lie algebra is arising from this infinite dimensional Lie algebra A. A is the subalgebra with the sum of two index EMN to be the even. It is the subalgebra of GL infinite. So from this A, we consider this Affine Lie algebra A hat. So the additive group of integers on A can lift into the actual automorphism group of A hat, and we can define a linear character from this group Z to a set of non-zero complex numbers. After define this group character, we can prove that the trigonometric Lie algebra of type A is isomorphic to the covariant algebra of the Affine Lie algebra A hat, and the group action is this Z with this group character chi Q, and we can find the concrete correspondence from the generators of trigonometric Lie algebra A of type A, that is A alpha M, to be these elements in the quotient algebra of Affine Lie algebra. It is the covariant algebra in the covariant algebra of the Affine Lie algebra. So similarly, we can find other group actions and group character to realize the type B and the type C trigonometric Lie algebra as the covariant algebra of this Affine Lie algebra A hat. We can realize B and C. Also, we can prove that type C can also be realized as the same covariant algebra like B. So from this realization, we see that the type B trigonometric Lie algebra is isomorphic to the type B case. So the last is type D case. Type D, we know from, I will say more words about the type D because it is related to the Q-versorial algebra we studied earlier. The type D trigonometric Lie algebra has these generators called D alpha M and has such Lie relations. It is the fixed point of the trigonometric algebra of type A with the involution tau D. And if we consider this A's D subalgebra, we can prove that this type D trigonometric Lie algebra is isomorphic to the covariant algebra of this A tau hat, this Affine Lie algebras. And the trigonometric Lie algebra of type D is as after this realization, we find that this type D trigonometric Lie algebra is isomorphic to the Q-Virasoro algebra in the study of the lattice conformal theory, which was introduced in these physics papers. And the Q-Virasoro algebra is a deformation, Q deformation of the Virasoro Lie algebra. It has the generators d alpha n and a center with these relations. So from this relation, it is not clear that it is not clear to see that it has some relations with Virasoro algebra. In fact, this Q deformation occurs in the Fermi realization of Virasoro algebra. This d alpha n just a symbol. Its deformation, in fact, is essentially occurs in the Fermi realization of the Virasoro algebra. So it is called the Q-Virasoro algebra. So this algebra we studied in 2019, and also we studied this Q-Virasoro Lie algebra in the context of the Vertex algebra, and we get an interesting result is that when this Q is primitive order root of unity, then the Q-Virasoro algebra, now we also can call it trigonometric Lie algebra of type D, is isomorphic to the Affine Kac-Moody Lie algebra of type B. That is, it has these relations with Affine Kac-Moody Lie algebra from for the Q-Virasoro algebra. Now we can associate the trigonometric Lie algebra and the Vertex algebra, because we have a realization from the trigonometric algebra as the covariant of Affine Lie algebras. Now, here we proved that if Q is not a root of unity, then the restricted module categories for the trigonometric Lie algebra of type A has correspondence to the equivalent Quasi module category of this Affine Vertex algebra arising from this Affine Lie algebra A hat. So this is its module correspondence. Furthermore, if we consider this L A hat L0 to be similar to the Affine Kac-Moody Lie algebra case, we consider this L A hat L0 to be the simple quotient of this universal Vertex algebra. Then we can prove that this is an integrable module for this Affine Lie algebra A hat, if and only if this L is a positive integer. And furthermore, if this L is a positive integer, the module category for this simple vertex algebra L A hat L0 corresponded to the integrable module category, restricted integrable module category for this Affine Lie algebra. And as I mentioned that Katz and Riddle, they classified all the unitary highest weight irreducible module for this trigonometric Lie algebra of type A with finite dimensional weight space in this paper. So based on their results, we associate this module category to the vertex algebra module category. We proved that if this L be a positive integer, then every unitary Quasi finite highest weight irreducible module classified by Katz and Radel for this trigonometric algebra of type A is an irreducible equivalent quasi-module for this simple vertex algebra, LA hat L0. So similar to the type A case, we have the association of the trigonometric algebra of type B to the vertex algebra, and the type because C and D are the isomorphic for the trigonometric algebra. So BOC, we have this restricted module category for this trigonometric algebra to the equivalent quasi module for this Affine vertex algebra with level 2L. We have such module category correspondence for type B case. And also last one is the type D case that restricted module category for the trigonometric algebra of type D has correspondence to the equivalent quasi module for this Affine vertex algebra arising from A tau. It is A tau hat. It is the fixed point of tau A. So this is the association of all the trigonometric algebra and the vertex algebra. Finally, I want to present our recent result when we consider this Q to be the root of unit case because it motivated by the Q-Versora algebra. We know that Q-Versora algebra is isomorphic to D type, and we find some relation between the Q-Versora algebra and Affine Kac-Moody Lie algebra. So we want to know how the relation between this A type, B type to the Affine Kac-Moody Lie algebra, if there is such relations. So when this Q is the primitive order root of unity, we can relate this A type, B type, and D type to the Affine Kac-Moody Lie algebra. It can give their realizations. And but for the even root of unity, it's more complicated. It is not isomorphic to the exactly Affine Kac-Moody algebra. It will isomorphic to some the quotient of this algebra. So it is more complicated, and we are working now. We are working now. It is an ongoing work. So, okay, that's my talk. Thank you very much.
Thank you so much, Qing. Let me stop the recording.
Okay.